Hey everyone, Sebastian here, and I wanted to make a quick video about a sandwich attack that recently happened on the MinSwap protocol for Cardano. Now, this was a small attack, but I thought it was interesting to talk about because a lot of people wanted to know how this happened, why this happened, and I thought it tied in really well with some other topics that Axo, for example, another DEX for Cardano, has talked about, and some topics in kind of greater crypto ecosystem. So before we get into exactly what this sandwich attack was, I'm just going to go over some very brief background onto why dexes work the way they do inside blockchains. So first, imagine you have some kind of S coin, and you want to sell these S coins. So you say you want to sell 50 of them at $4 each, and you put this up as a sell order. You want to sell this. So one way you could write a DEX is that everybody can see all these sell orders that exist. And if you want to buy some S coins, there might be a bunch of orders at different prices. And maybe for this one, we'll also make it 40. And there might be, some fairly big difference in price between them. And so you would choose which of these orders you want to pick, and then you would be matched against this specific person. So let's say you want to buy 50 of them, you would match against this specific order, and if the amount and the dollar matches, then your order gets matched, and you've purchased 50 S coins at $4 each. Now, as you can imagine, this is a very inefficient system for blockchain use cases, because if you wanted to buy something at like 4.75, then there's no order for 4.75. There's a price difference of 0.5 coins per token, for $0.5 per token between each order. And so this is not a great system. So the way people have managed to solve this while still being in an architecture that works well with blockchains is with some automated market making, where basically there's liquidity providers and they come in and make sure there's enough liquidity at any given price, so that if you want to come in and you want to buy a token, instead of trying to match against a specific order, you instead give a price. So say you want to come in and purchase for 4.75. You want to buy 20 of them. This is what you want to buy. What it does, it basically tries to match you against these liquidity providers at the best possible price for you. Now, there might not be any order at 4.75, so usually you specify some kind of slippage. So you might specify maybe like 1% slippage maximum, so that if the price falls to 4.70, for example, this is your order still goes through and you still get the tokens, even though there's not exactly the price you wanted. And this slippage makes that it's easy to make your order go through, even though there might not be any available at the exact specific price that you were asking for, that you were looking for. But this kind of slippage system is actually slightly problematic, because what happens if you want to buy a token? So imagine that you see S coins on a DEX, and you see that S coins are listed at currently 4.70. Okay, you see this on the website, and so you come in and say, okay, I will buy at 4.75 with a 1% slippage, and you would hope that because the price is under a 1% difference, that your order would go through and you get access to your S coins. But what might actually happen is that somebody else comes in and buys the S coins before you do, which raises the price to maybe 4.77, and then they sell the S tokens for you at 4.77, which is still within your tolerance, and then you now get your S coins. So you still got the coins you wanted, but the price you managed to buy them at is different. And so, this is not ideal for you as a buyer, because you lost a certain percentage of potential coins that you might have gotten had this not happened. And what makes this situation even worse is that it's possible for all these three things to happen inside the same block. So remember, blockchains, are a set of blocks, and these blocks have some time between them. So for example, in Cardano, this is on average 20 seconds. So it's not instantaneous. There's actually, a decent amount of time between each block. So let's say that, this block here just finished and you put in your order right there. Some other malicious person, might come in and, okay, there you go. Some other malicious party might come in and see your transaction, put in a transaction before yours, and then put another transaction after yours. So the transaction that comes before you is the one that purchases these tokens, and then the one that comes after you is the one that sells these tokens back to you at a higher price. So this is essentially what is called a sandwich attack, because for the blue person, this was basically risk-free. As long as they see that you are in between their buy and their sell, they know that they can purchase for a price and then sell it for another price right afterwards, all within the same block when this executes in the next block over here. So now you can see that, sandwich attacks are not ideal, because, not only does it give it a worse experience for the person who's trying to buy these S tokens initially, and so it's for them it's kind of frustrating, but also it's really motivating for attackers to attempt this, because if you are trying to create sandwich attacks, every sandwich attack you manage to pull off is basically guaranteed profit. So you have a strong incentive to try and look for these sandwich attack opportunities and take advantage of them when you can. So now that we have some background about what these sandwich attacks are and why people do them and why they're so common, now let's look at how different protocols and different dApps are trying to tackle this and the different trade-offs you get. So first, you'll notice that the whole premise of the sandwich attack is that we had a bunch of transactions come in, and then they all got included in the next block, all as an atomic operation. So when we mentioned the sandwich attack had a person in blue, right, that was the one making the attack. The person making the attack might also be the person making the block. So they can take advantage of the fact that they're making the block next to know for a fact they can include their transactions inside in a specific order. So this is obviously not great, and there's a few different protocols. Sorry, my color is kind of being weird. There's a few different protocols that are trying to tackle this situation to avoid giving too much power to the upcoming block producer, to make sure that they can't take advantage of the fact that they know they're going to make a block next to pull off sandwich attacks. Now, in the MinSwap case, the attack was not caused by a block producer, it's not caused by a stake pool, but it could be caused by a stake pool in the future if a stake pool decides to try and act maliciously in this way. So two protocols that you might have heard of that try and get around this is PBS, which is an Ethereum protocol, and then input endorsers, which is one for Cardano. And the point of these protocols is to basically split up the responsibilities. That way, the person who chooses the order of the transactions is different from the person who makes the block, which discourages and reduces the opportunity for somebody who's a block producer to take advantage of their privileged position to pull off this kind of attack. So this is one way to tackle the problem, but at the end of the day, somebody's still picking transactions, so it doesn't get rid of the problem entirely, but it's still something that people are definitely investigating. But one thing that you might know if you've ever developed a Cardano smart contract is that it's very hard to get stuff order by time. Like one way you might be tempted to solve this problem is you say, okay, well, instead of ordering transactions arbitrarily, we'll somehow sort transactions by the time that they were created. The problem is that you can't know the time a transaction is created. The only thing you can know is the time it was included inside a block. And so this makes it hard to order by time, because you don't know when these three transactions were created time-wise, and they could come in any order that's possible. What you do have access to in Cardano is something called time to live. So it's a range of how long the transaction is valid. Now you might have a range from 0 to 200, and what that means is that this transaction is valid from block 0 all the way up to block 200. And this is not necessarily ideal because it means that in the case of, for example, a sandwich attack, if there's any opportunity to sandwich this transaction within this 200 block range, a block producer could decide to withhold your transaction, censor the transaction, not put it inside the blockchain until a sandwich attack opportunity comes up, and then decide to include your transaction. So to avoid this happening, you can specify a short range. So you could say that the time to live for this transaction is block 0 to block 2, for example. And now there's not much time to have your transaction go into a block. And if it passes this time, if we go past block 2, the transaction becomes invalid and it can no longer be posted to the blockchain. And so as a protocol, as a dApp creator, you want to specify the smallest range possible to lower the chance of a user's transaction being withheld until an opportune time. But the other problem is that the smaller the range you make, the higher the chance a transaction may fail just because it timed out. Like maybe the transaction got sent to a server which was busy, and that server didn't have time to respond to their transaction for 40 seconds. And as I mentioned, the block time for Cardano is 40 seconds. So it'll expire not because it was maliciously being withheld, but just because the time expired. So now you get some idea of kind of the difficulty of handling time on Cardano to avoid this kind of issue, which is precisely what Axo DEX on Cardano has talked about in the past. Now there are some ways you can tackle this and get around Cardano's limitation. And one of the ways you can do this is by making the blockchain itself faster, right? So as I mentioned, Cardano's blocks are 20 seconds, which gives quite a lot of time for people to find sandwich attacks, commit sandwich attacks, and then take the profit. But what if you made the blockchain so fast that it's very hard to pull off this attack, because by the time you learn about the transaction, it's already submitted and already on chain. And that's kind of the thought process of Solana. So for Solana, they had their block times is around 400 milliseconds, if I remember correctly. And part of the marketing for Solana was that it was meant to be NASDAQ scale. So if you're wondering, why they kind of chose that wording, it's partially for this reason, right? They want to have a blockchain that was fast enough that you could not easily react to user actions, because by the time you learn about them, they're already on chain. Obviously, this comes with a lot of decentralization trade-offs, because 400 milliseconds, as you may know, if you have the globe and you have different continents on the Earth, the time it takes to go around the Earth is a double-digit milliseconds. So it's very hard to build a true decentralized network with 400 millisecond block times. So there's other blockchains like Algorand that try and put more emphasis on decentralization, but still have a block time of around 4 seconds. So they still try and be faster. But it'd be nice if you could tackle this problem without having to speed up your blockchain, because it obviously has potentially negative effects on decentralization. It also increases the size of your blockchain as well, which hurts decentralization in its own way, because now the storage cost of the blockchain is higher, for example. So if you don't want to speed up your blockchain itself, then another option for you to look at is layer 2 solutions. So there's two notably that we can talk about. Is one Hydra, the other one is rollups. It's kind of two examples of potentially a potential solution. So when I say Hydra, I mean state channels. Now, why would these two different layer 2 options help with this situation? Well, for Hydra, the essential idea of Hydra is that you open a state channel, and this is on mainnet. So let's denote these mainnet blocks by red blocks. So this is a block that happens on the main chain. So you open a state channel, and then you make blocks at a very fast interval. So you see on our state channel, the block time will be 1 second. And you can afford to have a faster block time because a state channel is usually between a fixed known set of people that are online all the time. So you can know all these people are online, they're actively monitoring the blockchain, and we know exactly who they are. We can easily get blockchains 1 second. You can even get block times like 300 milliseconds if you want, as long as you know all the parties in the state channel can do this. And so you do a bunch of transactions at a much faster time, and then at the end you settle on the blockchain when required. And so this allowed you to have much faster block time, which avoids the chance of any kind of sandwich attack happening, while keeping the layer 1 blockchain at the same block interval of 20 seconds, for example, for Cardano. Now, the problem with Hydra and state channel solutions is, as I mentioned, it requires the parties to be online and these parties to be known in kind of the general implementation. Now, there's ways you can modify Hydra, improve Hydra to get around these limitations, but the base concept of a state channel, has this kind of property, and this makes it very hard to use for something like a decentralized exchange, which is fairly global in nature, where you don't have a fixed set of people. You're trying to trade tokens with unknown parties at unknown times. So Hydra, can tackle this problem, and state channels can tackle this problem, but it's very hard to use any kind of state channel solution for a DEX. It's not really the ideal use case for these technologies. So another solution you might be tempted to try is a rollup. So rollup is different than Hydra. So Hydra is not one global system. As I mentioned, it's something you create between you and a set of known parties. Rollup is a global network that continues to exist. So you might have your blockchain down here, and you have your layer 2 solution rollup up here, and the layer 2 occasionally submits its state down into the layer 1. And so the state of your layer 2 system is entirely embedded inside your layer 1 solution. Now, the reason people often don't really go towards rollups or these kinds of solutions for this problem is because if you look at this graph, the entire point of a rollup type solution is that you post the state of the network inside the layer 1 solution. And so if your blockchain is already running at 28 seconds, then your layer 2 solution, your rollup, is usually also running at 20 seconds as well. It runs at the same time as the underlying blockchain. And that's what people usually mean when they say it inherits the security of the layer 1 blockchain, because you take advantage of the fact that as long as these layer 1 blocks are being honestly produced, the layer 2 system will also be honestly embedded inside these blocks. So, because of this, the rollup solution is obviously not an ideal solution for tackling this problem, but it is possible to create a rollup that has faster blocks than layer 1. And the way you would do it is you would, post like other rollup blocks between the main ones, and you would say that these like partway through rollup blocks are just not finalized. They don't inherit the layer 1 finality, but they still exist. And this is fairly tricky from a technology point of view to get this working, and whether or not people trust these assertions of the finality of these like in-between blocks is also not so clear. So this is not a great solution, but it is something that people definitely have thought about in the past, have attempted in the past, but I don't think any of them have super taken off currently. It does not mean they may not take off more in the future, but it's proven to be a little difficult. So, given all of this, we have a few different options, but none of them are perfect. All of them have trade-offs. And because of that, I want to talk about, 2 other different options that work kind of in a general case, and a third option that you have primarily for Cardano. So the first one is some kind of fee market or a transaction prioritization, so that the ordering of the transactions is not purely up to the block producer. If you say like, oh, the transactions must be ordered according to some prioritization logic, or they must be ordered according to a fee, then it's becomes harder to pull off a sandwich attack if the sandwich attack does not follow the prioritization rules of the blockchain. So this is something that people have definitely looked into and attempted in various ways. But oftentimes these kinds of prioritization algorithms don't solve this problem. They introduce instead other different kinds of sandwich attacks that instead just are limited to follow the prioritization rules. The benefit of these systems is not so much that they get rid of sandwich attacks, but the fact that you, by defining the prioritization on chain, possibly, for example, via fee market, even though the sandwich attacks may still occur, you can set up so these sandwich attacks benefit the average ADA holder more than the attacker. So, for example, in the more concretely, in the example we saw earlier in this video, I showed an example where an attacker, bought at a small price and sold at a higher price, and they took all the profit. So all the profit went to the person blue, who took all the profit of pulling off this attack. If you have some kind of a fee system and you have multiple people trying to do sandwich attacks, then for them to guarantee their sandwich attack is the one that goes through, they will pay a higher fee, and these higher fees get paid to the average Cardano holder and the Cardano treasury. So it means that if you pull off a successful sandwich attack, instead of all the profit going towards the blue person, they may be able to take some of the profit, but a lot of the profit goes back into the Cardano treasury and into the general Cardano holder. So it helps kind of democratize any profit from this kind of attack when they arise. So that's why people, investigate these ways to tackle the problem. And then another way is to try and have faster finality. So another kind of way you could do a sandwich attack is if you find a way that a sandwich attack can be executed, you could try and have a small rollback of the blockchain. So you could say, like, okay, I know that if I take the transaction that occurred here and roll back the chain, change the state of Cardano so that the transaction occurs in the previous block, then I can sandwich them. And so there's a chance that these kinds of rollback attacks occur. Of course, they're unlikely in a fully decentralized network where everybody's being an honest actor, but technically it's still possible for somebody to leverage rollbacks to increase the amount of sandwich attack opportunities or other attacks like it. But a fast finality protocol will mean that it's harder to do these attacks because finality, if you don't know, in the blockchain context means that, for example, this block cannot be rolled back. Once it exists, it's finalized and cannot be undone, and therefore you cannot attempt to time travel to pull off sandwich attacks. So this is the benefit of protocols like Algorand that have instant finality, because once the transaction has settled on layer 1, it can't be rolled back, so you can't attempt these kinds of time travel attacks. Cardano has a fairly long finality, same as Bitcoin and any other kind of Nakamoto consensus chains, and BFT protocols like Algorand usually can have faster finality. There's some blockchains that have kind of in-between options, like Ethereum is Nakamoto consensus, so like Cardano, it usually would have a long finality, but they have some algorithm on top of it to make that it has fast finality when there are a lot of honest actors present and online in the system. So this is, some way people are potentially leveraging fast finality to get around this kind of issue. So these are two other things to consider. By the way, in Cardano, if you ever want faster finality, then Cardano provides dcSpark as a library called Multiverse, which gives you faster finality for your Cardano dApp. So that might be something you're interested in. But a third solution that's slightly unique to Cardano, I wouldn't say it's entirely unique to Cardano, but not that many chains do this, is to have a fail fast approach. So one thing that we didn't discuss, but is entirely reasonable as an option, is what if you made that this person here, the person that got sandwiched, they create a transaction that says try and detect if I'm getting sandwich attacked, and if I'm getting sandwich attacked, just fail the transaction, just don't execute it, walk away. And this would reduce the amount of sandwich attacks that occur. The reason a lot of other chains cannot do this is because in most blockchains, like for example for Ethereum, running this kind of code to detect if you've been sandwich attacked. If you've been sandwich attacked has a gas cost. And so if you end up getting sandwich attacked and you have to pay a high gas cost to execute the transaction, and then you also end up getting no tokens, this is not a great solution. And so the ideal solution for this would be some kind of fail fast mechanism where if you detect a sandwich attack, not only do you abort your transaction, but you also paid no transaction fee. And actually Cardano has this system in place. So in Cardano, whenever a transaction gets executed, there's actually two phases. There's phase 1 and phase 2. And if your transaction fails in phase 1, then it will fail without costing you any gas cost. And only in phase 2 does the failure actually cost you ADA with the Cardano token. So you could design your protocol that in such a way that it detects, if a sandwich attack has occurred, and if so, fail your transaction during phase 1 validation, and ensure that you don't pay any transaction fees as a way to get around any potential sandwich attack. Now, if I got into this in this video, I think it would get probably too long, and it's already gone probably long enough. So I won't talk about it too much, but this solution also has quite a lot of negative downsides, which is why many people implement it. But it's definitely an option that you could provide for users that want this kind of property. So we went over, the sandwich attack in MinSwap, why this happens, why this is relevant to not just Cardano, but the great ecosystem, and quite a large variety of different ways people are tackling this problem. And so hopefully you've learned something new in this video. If you have any follow-up questions, definitely comment below. And if you have any other topic you'd like us to cover, definitely let us know. We're always looking for more educational content to put out on our channel, and we love to teach you all about blockchain. And if you want to learn more, definitely subscribe to our channel and check out our future videos.